In 2018, the Nobel Prize for Physics was awarded jointly to three people: Gerard Moreau, Donna Strickland and Arthur Ashkin for their work in the field of optics. Of these three, Arthur Ashkin won it specifically for his groundbreaking work from the 1970s in optical tweezers. But what are optical tweezers, and why did it win a Nobel Prize? Optical tweezers is basically the idea of manipulating matter with light by using the fact that electromagnetism, either in the form of a wave or particle as a photon, has an associated momentum. Since it has a momentum, then it can exert a force onto the matter it interacts with. At the large scales of day-to-day life, this force is negligible. Otherwise we would feel a pressure from the light of the sun anytime we went outside. Once we get down to the scale of microns and microparticles, suddenly it can overpower the force of gravity. The movement of light into a cell or bead results in an applied momentum whose magnitude is dependent upon the intensity of the light and refractive index of the target. Laser intensities are best described as a Gaussian, which means that this becomes a gradient force outside of the centre of the laser that points in the direction of higher intensity. Therefore, if the target gets knocked out of the centre of the laser, a restorative force is applied to correct it. Optical tweezers have been incredibly useful to biologists, who can use the technique to manipulate individual cells. What you're seeing here is a single red blood cell being moved. They're not the only ones making use of the technology though. Physicists in the field of quantum computing can now arrange individual atoms with light, and nano-engineers can produce structures molecule by molecule. Glasgow University's ARC building has its very own optical tweezer setup, where we can see it in action.
Basically optical tweezers is pretty much an actual inverted microscope, but with the ability to inject laser beams into the objective so you can actually trap things. So this is just a standard 2 micron silica beads in water. So basically we should be getting a laser trap pretty much in the middle layer. I'm just going to move one of the beads up. You can see it just blocks in. You can actually see it sink. It holds it fairly. You can move the stage quite fast actually, and it doesn't really kind of fall out of it. But the thing that comes with the optical tweezers is a secret. That's basically your simplest optical tweezers, a simple laser and create a trap, and you can move the sample relative to the trap around. But this one can actually grab hold of the marker and actually move the laser as the mouse. Okay, so I can basically just look at that part of the image there, and you can actually see the red dot there is the estimation of the centre of enhance. The point is, if you just look at a small part of your image, then you can actually go at several kilohertz, and that's where you really need to get a lot of microbiology measurements. So if you want to use a trap bead to go and measure viscosity of something, then you're looking at measuring the Brownian motion at sort of kilohertz or a few kilohertz frequencies, and that allows you to very quickly, with just a few seconds worth of measurement, and actually calibrate the force, the spring constant, and actually go and use that as a measurement probe. You can move around the sample and get a measure of either the forces or in terms of viscosity or things like the viscoelastic properties of the materials. So essentially for most things it's a non-contact ability to trap and manipulate things. So you've got a completely non-contact system. I mean, the biggest things that we've ever trapped is things like stem cells. They may be about 20-25 microns diameter as opposed to 2 microns. They trap fairly well. And I think maybe things that are maybe bigger that have been trapped, probably we haven't done it in the heart cells. They tend to be a bit bigger. But red blood cells, for example, I think they're about the same, between 2 and 5 micron. And so see, these are things that we'll tap before.
Hopefully this has shown you how powerful the study of optical tweezers has been, its rich background, its current uses, the potential futures for the technology, and why it won a Nobel Prize 5 years ago. If you're interested in photonics and want to see even more topics and exciting new technologies emerging, then check out the CDT for photonic integration and advanced data storage.